So in 5.2, we're going to continue working with our trig identities. And our goal, just like how it was in 5.1, is to simplify one of our trig equations. However, in 5.2, the difference is that we'll have like one equation's equal to another, and our goal is to simplify one side to get it to look like the other side. So in my opinion, 5.2 is a little bit easier because it kind of gives you some type of direction to follow. You know where and when you reach the end point. So down here we have some guidelines for verifying trig identities. We want to work with one side of the equation at a time. It's better to work with the side that looks more complicated first and simplify that side. And let's see, what else is important here? Always try something. Super important here. Always try something. If you look at it and you look completely lost, just attempt to try something. Whether it's change everything to sine and cosines first, change them so they're not fractions. Always try something. Because most of the time, if you attempt to do something, it kind of can lead you somewhere where you may know what to do next. So always try something. So let's look at our first example. When solving these, again, you want to have your trig identities in front of you. So just like how we did proofs in geometry, we're doing proofs with trig identities. So we want to separate this, and we're going to work one side at a time. So it said we want to start with the side that looks more complicated. What do you think looks more complicated, the left or the right? The left. So let's try to simplify the left side first. What do you think we should do? Where can we start?
We get rid of secant squared theta at the bottom.
We could. What are our trig identities, or what's the trig identity that involves secant? Anybody remember? Got it in front of you?
Subtract the 1.
Subtract the 1. Awesome. So we have tan squared is equal to secant squared minus 1. So we can take this secant squared minus 1, and make it a tangent squared. So now we have tangent squared theta over secant squared theta. If we want to, we can write sine squared every step of the way here, but we don't have to. We're just leaving that for last. We want to change our left side to look like a sine squared, so we don't have to write it each step. We can just, once we get sine squared down here, we can check that sine squared is equal to sine squared. They're the same. So you don't have to write it every step of the way. What should we do next? Remember, if you get stuck, maybe we can change these to sines and cosines. So in terms of sine and cosine, what would tangent squared be?
Sine squared over cosine squared.
Sine squared over cosine squared. And then what's secant squared in terms of sine and cosine?
1 over cosine squared.
1 over cosine squared. So now we have a fraction divided by a fraction. So what can we do? If we had, let's say,
Do you multiply it by cosine over 1?
yeah, so if we had, think about it in numbers. If we had 1/2 divided by 3/4, we would keep, change, flip. So we're doing the same thing here, but just with sines and cosines. So we keep the first term, change it to multiplication, and flip the second. Do you notice anything about what we have now? We have sine squared theta over cosine squared theta times cosine squared theta over 1.
Now you can just cross them out, right?
Awesome. We have a
Cross
cosine on the
multiply.
top and a cosine squared on the bottom, so they cancel. We have one on the top, one on the bottom, they cancel. So then what are we left with? Sine squared theta. What was our goal to get? What did we want
To
this
get
to?
a sine
Sine
squared.
squared theta.
Sine squared theta. So sine squared theta is equal to sine squared theta. Perfect. Which side do we want to start working with, the left or the right? The right. We always want to start with the more complicated side. So what should we do first?
Get rid of the fractions.
We can get rid of the fractions. Our goal is to simplify and make smaller because we see we have one term over here. So eventually we're going to get this to be one term. How can we combine these two fractions together? What do we need in order to add fractions?
Like terms.
The same denominator.
Yeah, that.
So how do we get these to have the same denominator? What do we have to do to the first one? Or what do we want our denominator to be?
You
What?
have to multiply it by the other one.
Yeah.
The
So
other-
our same denominator is going to be 1 minus sine. Instead of writing alpha, I'm just going to do theta because I can't write that. And then 1 plus sine theta. So on the top here, we have to multiply it times the other one. So 1 plus sine theta. And then this one, we're multiplying it 1 minus sine theta. So technically, we're multiplying the top and bottom here by 1 plus sine theta. And same with this one, 1 minus sine theta. Everybody with me so far? So I'm multiplying the top and the bottom here by the same thing. So we get the common denominator of 1 minus sine theta times 1 plus sine theta. So what would our top be on the left side when we have 1 times 1 plus sine theta? Just 1 plus sine theta. And then we have 1 minus sine theta. Are you with me so far?
Yeah.
Well, we can condense it. Olivia said combine like terms. So we have a 1 plus a 1, so that would give us 2. What happens to sine theta minus sine theta? On the top. It cancels.
Cancels.
So we have 2 on the top. And then what should we do on the bottom? We want to condense this. So how are we going to multiply these together?
So it just cancel out.
They don't just cancel out. It would be like saying 1 minus x times 1 plus x. So they don't just cancel, we have to FOIL them. So always think back in like algebra terms if the trig functions are what's confusing you. So we need to FOIL these together. So we multiply the first terms. So 1 times 1 is 1. Then the outsides, 1 times sine theta is sine theta. Then the insides, minus sine theta. And then the last terms. So what's negative sine theta plus sine theta? I mean, what's negative sine theta times sine theta? We're multiplying them.
Is it negative sine 2 theta?
Perfect. Negative sine squared theta. It's that sine that's squared because we have 2 sines. All right, how can we simplify this? Combine like terms. So our sine theta and negative sine theta cancel. So we have 2 over 1 minus sine squared theta. what would you do next here?
See what identity is the bottom one.
Awesome. What identity involves sine? Or sine squared. What identity involves sine squared?
Sine squared plus cosine squared equals 1.
Sine squared plus cosine squared equals 1. So can we manipulate this sine squared plus cosine squared equals 1 to 1 minus sine squared? Yeah. How do we do that?
You move the cosine over and the 1.
Our goal is to get 1 minus sine squared. So what do we need to do?
Oh, you did minus sine.
Minus the sine squared. So we subtract sine squared. So yes, I think it was Paula that said it. It's just cosine squared. So we substitute that 1 minus sine squared theta in place of cosine squared. So we're putting the cosine squared in place of that. So now we have 2 over cosine squared theta. Remember, our goal, every once in a while, look back up to where you're trying to go. We want it to be 2 secant squared. So how can we change this cosine squared on the bottom to become a secant squared? Not keep, change, flip. What's 1 over cosine changed to?
Secant.
Secant. Cosine and secant are reciprocals of each other. So instead of just 1 over cosine, we have 1 over cosine squared, or 2 over cosine squared. So to bring it to the top, it becomes a secant squared. So even though it's cosine squared, we can still apply the reciprocal property. So we bring it to the top and it becomes secant. So perfect, we got 2 secant squared and 2 secant squared. Example 3. Which side are we going to work with, the left or the right? The left. The left one looks more complicated, so let's work with the left. Awesome. Tan squared plus 1 turns into secant. What is our identity for tan squared? Tan squared theta plus 1 is equal to secant squared. So tan squared plus 1 is just secant squared. So we're going to put in secant squared there. Secant squared x. Now for the one that involves cosine squared, that is sine squared x plus cosine squared x is equal to 1. How can we make this look like cosine squared minus 1?
You just subtract.
So we want to move the 1 over and move the sine over to the other side. So it becomes cosine squared x minus 1 is equal to negative sine squared x. So just remember, when you move it over, you're subtracting. So we have to have that minus sine squared. So what are we going to put in place of cosine squared minus 1? Negative sine squared x. What can we do next? Change secant squared to 1 over cosine squared. what should we do next?
Do you multiply them?
Let's multiply. So we have negative sine squared x over cosine squared x. Remember, our goal is to go back to negative tangent squared x. What do we know about sine over cosine?
Becomes tan.
It becomes tangent. However, both of these are squared, so it becomes tangent squared. So we have a negative tangent squared x. Is that what we were trying to get? Yep, so we are done. Perfect. So some of these just require a couple steps, some of them require a lot more steps.
Ms. Carver, can you go back to the last?
All right, let's look at number 4. So we want to verify the identity tangent x plus cotangent x is equal to secant x times cosecant x. So which side do you think looks harder here? Which looks more complicated? Just take a guess. What do you think? Left or the right? Left. I would say the left looks a little bit harder just because it's 2 terms instead of 1 term together. Because we're adding the 2 instead of multiplying them. So let's work with the left. Where do you think we should start?
Tangent x equals sine x over cosine x?
Yeah.
Like, could you do that? Okay.
Yeah, so tangent is sine x over cosine x. And then what's cotangent?
Cosine x over sine x.
Perfect. Cosine x over sine x. So we have 2 fractions here, and we want to get 1 term. So how can we combine these fractions? What do we need? The same denominator. So what could our same denominator be?
Would you have to multiply cosine x to both of them?
So our goal is to get the denominator to be cosine x sine x. So on the one on the left, we need to multiply the top and the bottom by sine x. And on the right, we're going to multiply the top and the bottom by cosine x. So what's sine x times sine x?
Cancel.
Sine x times sine x cancels? Sine squared x.
Squared, yeah.
And then what's cosine x times cosine x? Cosine squared x. And then the bottom's just cosine x times sine x. Everybody with me so far?
Yes.
Any questions yet? What do we notice about the top here, our numerator?
It's an identity.
It's an identity. What's sine squared x plus cosine squared x?
1.
1. So we have 1 over cosine x times sine x.
And then that just simplifies to secant x and cosecant x.
Awesome. So looking back, our goal is to get secant x times cosecant x. We see that 1 over cosine is secant x, and 1 over sine is cosecant x. So that's equal to secant x cosecant x. Good job, guys. All right, so which side looks harder? Which one do you want to work with first?
Definitely the right one.
The right one. All right. So what should we do first?
Is it an identity?
It would be an identity if it was squared, if it was 1 minus sine squared, but it's not. We did one of these, I think it was yesterday, where,
Miss Carver?
yes,
Would it be the same thing as last time? Would it be like a quotient identity?
do you mean like when we had cosine over sine and we changed it to cotangent? Like that?
Yeah, would it be something like that?
We can't do that because we have two terms in the denominator. So we couldn't,
Oh.
we can split them up if we have one term in the denominator. So let's say we had, just as an example, we had 1 plus 3 over x. We can change this to 1 over x plus 3 over x. But if we had two terms in the denominator, if we had, let's say 2 over x plus 1, we can't separate this. So we can separate it if there's 1 in the denominator, but can't separate it if there's 2. So we have two terms in the denominator, we can't split it into 2. We did one like this yesterday, and the example in the algebra example that I gave you was, let's say we had 1 over 3 minus I. How do we get rid of that I in the denominator?
You multiply by the 3 plus I?
Plus
Yes, we multiply it by its conjugate. So we would multiply it by 3 plus I. So what would be our conjugate here for 1 minus sine?
1 plus sine.
1 plus sine. So what we do on the bottom, we have to do on the top. So on the top, we get cosine x plus sine x cosine x. And what do we get on the bottom? How do we multiply that 1 minus sine x times 1 plus sine x? FOIL. So we multiply the first ones, the outsides, the insides, and the last. What's negative sine x times sine x?
Cancels. Oh wait, no, it's sine squared x.
Negative sine squared x. When multiplying, they don't cancel. So sine x times sine x, you have two sines, so it's sine squared x. So now, positive sine x and negative sine x cancel. And on the bottom, we have 1 minus sine squared x. How can we change that 1 minus sine squared x on the bottom? What can we do? Use an identity. So our identity is sine squared x plus cosine squared x is equal to 1. How can we change this to 1 minus sine squared x?
Back sign.
Subtract sine squared. So we get cosine squared x is equal to 1 minus sine squared x. So now we can just plug in that cosine squared x for 1 minus sine squared. So we change this to cosine squared x. So we get, yes?
Does it matter, like, from when you're doing the numerator, like, I was doing, like, 1 and I wrote cosine x sine x, or do I have to write it sine x cosine x?
It doesn't matter. So when you're multiplying, it doesn't matter. You could write, that's a good question. So you could write sine x times cosine x or cosine x times sine x, same thing. So when multiplying, it doesn't matter the order. All right, what can we do next?
Cancel the cosine.
Awesome. We have a cosine on the top and a cosine on the bottom. So I'm going to take out the cosine on the top. We have cosine x, 1 plus sine x on the top, and cosine squared x on the bottom. Matthew says to cancel out one of the cosines on the top with one on the bottom. So,
Wait, Miss Barber, why did you put 1 plus sine x?
because I took out a cosine here. So when I take out a cosine, I made it back, look like how it started here before I distributed that cosine x to both of them on the inside.
Oh, okay.
So from the start, I didn't even have to distribute it. I did, but I just had to go backwards a step to take out that cosine. Because we have a cosine on the top and a cosine common on the bottom. So that cosine on the top cancels out with one of the cosines on the bottom. So now we're left with 1 plus sine x on the top over cosine on the bottom. What should we do next?
And identity.
Isn't it? Never mind.
Like,
Not an
Is it
identity.
1 over cosine x secant, and then sine cosine's tan.
Awesome. So just like I showed you on this one, how we could break it up, since we have one term on the bottom, let's break it up. So we have 1 over cosine x plus sine over cosine. So you said 1 over cosine is secant, and sine over cosine is what? Tangent. Let's go back to see what we were trying to get. Oh my goodness, secant plus tangent. That's what we got. So we're done. Any questions on this one? Alright, so number 6 says working each side separately. So we're going to have to do stuff on both sides, but we just want to be careful that we're only doing one side at a time. So the left side looks a little bit more complicated just because we have 2 terms on the bottom. So there's different ways we can approach this. We can change cotangent to be a cosecant using our trig identities. So our identity is 1 plus cotangent squared is equal to cosecant squared. So then we can subtract the 1 over. So cotangent squared is equal to cosecant squared minus 1. So we're going to change this out for cosecant squared minus 1. That way we have all cosecants on one side. Maybe we can see if we can get a little bit further this way. So we have cosecant squared minus 1 on top, and 1 plus cosecant, well, theta and theta on the bottom. So on the top, we have 2 perfect squares, the difference of 2 perfect squares. So we can actually split this up into cosecant plus 1, cosecant theta plus 1, and cosecant theta minus 1. So we have the difference of perfect squares on the top, so we broke it up into cosecant theta plus 1, cosecant theta minus 1. And then we have a 1 plus cosecant theta on the bottom. Well, we can see we have the same thing on the top and on the bottom. Cosecant plus 1 is the same exact thing as 1 plus cosecant. So these are the same. And since it's being multiplied here, we can cancel this out. So this is like saying, in terms of algebra, x times y over x. These x's cancel because they're the same. So then we're just left with y. So we have cosecant theta minus 1 that we're left with. So this cosecant plus 1 and 1 plus cosecant cancel. So maybe let's try to work on the right side now and see if we can simplify this. Because now looking at the left, we have it's simplified a little bit more. The right side's more complicated, so let's simplify the right and see if we can break it down. So since we only have one term on the bottom, we can split this up. So we have 1 over sine theta minus sine theta over sine theta. 1 over sine theta changes to cosecant theta, and then sine over sine simplifies to 1. So we have cosecant minus 1 and cosecant minus 1. Look at that. Same thing. Awesome. So sometimes you have to work on both sides when both of them look kind of complicated, and you can simplify it down to 1 or 2 terms here. You may have to work both sides, but just be careful that you're only doing one side at a time. You never want to move something from one side over to the other. So just be careful.